Hello everyone. Today we are going to talk about MotionLM, multi-agent motion forecasting as language modeling. The motivation for this research is rooted in the need to improve interactive motion forecasting. The current methods in use have shown limitations in adequately capturing the joint distribution over multimodal futures. This is a significant challenge as it directly impacts the ability to predict and understand complex interactive motion scenarios. Existing methods have been found to struggle with the complexity of interactive motion forecasting. They often face scalability and latency issues, which can hinder their effectiveness in real-time applications. Furthermore, these methods have been unable to surpass the previous top entry on joint map with a limited number of rollouts. This indicates a need for a more robust and efficient approach. The approach, detailed in this paper, leverages multi-agent rollouts over discrete motion tokens. This innovative method allows for a more comprehensive representation of the multimodal future distribution. However, despite its potential, it has been observed that existing methods may not be able to fully exploit this approach due to their inherent limitations. In conclusion, while existing methods have made strides in interactive motion forecasting, they still fall short in several key areas. This paper proposes a new method that addresses these limitations and pushes the boundaries of what is currently achievable in the field. The proposed method not only improves upon the state of the art, but also opens up new avenues for future research and development. The authors of this paper are addressing the challenge of interactive motion forecasting. This problem is significant as it involves predicting the future actions of multiple agents in a dynamic environment, a task that is crucial for applications such as autonomous driving. Previously, existing methods struggled to adequately capture the joint distribution over multimodal futures, which is a key aspect of this problem. These methods were also limited in terms of scalability and latency, and were unable to surpass the previous top entry on joint map with a limited number of rollouts. To overcome these issues, the authors introduced a new method that leverages multi-agent rollouts over discrete motion tokens. This approach allows for a more accurate representation of the multimodal future distribution. The method also involves clustering down to a specific number of modes for evaluation and uses a significant number of rollouts per replica for final leaderboard results. Through this approach, the authors were able to establish a new state-of-the-art performance on the WOMD Interactive Prediction Challenge. The authors also explored the use of their proposed method in model-based planning frameworks and the formation of a search tree over the multi-agent action rollouts. They suggested the exploration of distillation strategies from large autoregressive teachers to enable faster student models in latency-critical settings. These new strategies and insights have the potential to further improve the performance of interactive motion forecasting. Section 1. Problem formulation and approach. The authors of this paper have tackled the complex problem of interactive motion forecasting. They have formulated this problem as a multi-agent task, where the goal is to predict the joint distribution over multimodal futures. The authors have approached this problem by leveraging multi-agent rollouts over discrete motion tokens, which is a novel method that differs from previous approaches. This method allows the model to capture the diversity of multimodal future behavior without relying on trajectory anchors or static intention points. Section 2. Methodology and experiment design. The authors have designed a method that uses a sufficient number of samples from the model to represent the multimodal future distribution. They have clustered these samples down to k=6 modes for evaluation. The model uses 512 rollouts per replica for final leaderboard results, but it's found that 32 rollouts can surpass the previous top entry on joint map. The authors have designed experiments to evaluate the model's performance across varying interactive attention frequencies and numbers of rollouts. They have also evaluated the model's performance in terms of latency on the latest generation of GPUs across different numbers of rollouts. Section 3. Improvements and innovations. The proposed method has several improvements and innovations over previous approaches. Firstly, it establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge. Secondly, it allows a search tree to be formed over the multi-agent action rollouts, which is a novel application of this method. Lastly, the authors have suggested exploring distillation strategies from large autoregressive teachers for faster student models in latency-critical settings. This is a promising avenue for future research and could lead to significant improvements in interactive motion forecasting. Technical results. 1. State-of-the-art performance. The proposed model has established a new benchmark in the WOMD Interactive Prediction Challenge. This achievement signifies the model's superior ability to forecast interactive motion, outperforming previous methods. 2. Performance evaluation. The model's performance was evaluated across varying interactive attention frequencies and numbers of rollouts. This comprehensive evaluation demonstrates the model's robustness and adaptability to different conditions. Additionally, the model's latency was tested on the latest generation of GPUs across different numbers of rollouts, showcasing its efficiency. 3. Model variations. Different versions of the model with varying parameters were tested. The model with 9M parameters was used for the main results, while a model with 27M parameters overfitted and a model with 300K parameters underfitted. This indicates the importance of parameter tuning for optimal performance. Ablation studies and implications. 1. Rollout numbers. The model uses 512 rollouts per replica for final leaderboard results, but it was found that even with 32 rollouts, the model could surpass the previous top entry on joint map. This suggests that the model is effective even with a limited number of rollouts, demonstrating its efficiency. 2. Mode clustering. The method clusters down to k equals 6 modes for evaluation. This approach allows the model to effectively represent the multimodal future distribution, highlighting its ability to handle complex forecasting tasks. Key insights. 1. Future applications. The proposed method can be used in model-based planning frameworks, allowing a search tree to be formed over the multi-agent action rollouts. This suggests potential applications of the model beyond its current use. 2. Distillation strategies. The paper suggests exploring distillation strategies from large autoregressive teachers for faster student models in latency-critical settings. This indicates potential avenues for further improving the model's efficiency and speed. 3. Improved forecasting. The paper concludes that the proposed method can improve interactive motion forecasting by leveraging multi-agent rollouts over discrete motion tokens. This underlines the model's contribution to the field of motion forecasting. Key highlights of the paper. Key insights. 1. The paper introduces a novel method for interactive motion forecasting that leverages multi-agent rollouts over discrete motion tokens. 2. The proposed method can be utilized in model-based planning frameworks, enabling the formation of a search tree over multi-agent action rollouts. 3. The paper suggests exploring distillation strategies from large autoregressive teachers, which can lead to faster student models in latency-critical settings. Key contributions. 1. The paper presents a new approach to interactive motion forecasting, which significantly improves upon existing methods. 2. The proposed model establishes a new benchmark in the WOMD Interactive Prediction Challenge. 3. The paper also introduces a method for aggregating rollouts to uncover the underlying modes of the distribution and estimate the probability of each mode. Key idea. The central idea of the paper is to improve interactive motion forecasting by leveraging multi-agent rollouts over discrete motion tokens. This approach allows for a more accurate representation of the joint distribution over multimodal futures. Key results. 1. The proposed model achieves state-of-the-art results in the WOMD Interactive Prediction Challenge, with a 6% relative improvement in MAP and 3% relative improvement in miss rate over the previous top-scoring entry. 2. The model also shows a substantial improvement in miss rate over all prior works, with a relative 9% reduction compared to the previous state-of-the-art. Key conclusion. The paper concludes that the proposed method significantly improves interactive motion forecasting. Future work will focus on leveraging the trained model in model-based planning frameworks and exploring distillation strategies for faster student models in latency-critical settings.